University, and he is going to tell us about a continuous matrix product operator approach to finite temperature quantum state and its application to the nonlinear sigma model with theta equal pi time. Please.
So thanks for the introduction, and I would like to thank the organizers for giving me this opportunity to present my work here. So today I'm going to talk about this continuous matrix product operator approach to finite temperature quantum states and its application to the O3 nonlinear sigma model with theta equaling to pi term. So this work is done in collaboration with Professor Honghao Tu from TU Dresden and Professor Lei Wang from the Institute of Physics in Beijing and Professor Xinchen Xie from Peking University. So my talk will contain two parts. The first part where I will talk about our approach, which is the continuous matrix product operator approach. This approach is the tensor network method to study finite temperature quantum states. And in the second part, I will talk about the CMPO, basically this approach. We apply this approach to the 1+1 dimensional nonlinear sigma model with a topological theta pi term. And finally, I will give a summary. And so if we, when talking about quantum systems at finite temperature, common choice is for numerical simulations is the quantum Monte Carlo method. But for many interesting problems like the quantum spin system with frustration or many fermion problems, we will face the sign problem. So for this reason, people have been thinking about using tensor network algorithms to study the finite temperature systems. And the reason for that is the tensor network algorithm will have no sign problem. And to do that, people have working on very different routines. Here, I give a very incomplete summary of all these different methods. So at the beginning, people are thinking about to purify the density matrix into a pure state and then use the imaginary time evolution. We can also combine the tensor network state method with the Monte Carlo sampling approach. If we can take the partition function and as a tensor network, we can also make use of the tensor network contraction methods to obtain the partition function of the system. In that direction, there is the TRG method, and also we can make use of the transfer matrix approach. So our work actually belongs to this direction. We will represent a partition function as a tensor network, and we make use of the idea of the transform matrix to contract this tensor network to obtain the thermodynamics of the system. And the benefit of our approach is that we can work directly in the thermodynamic limit and the continuous time limit. That means we have no finite size effect and there is no time discretization error. Our method is also applicable to any Hamiltonian with MPO representation. That means we can apply our approach to long-range interacting systems and even quasi one-dimensional systems. And in our approach, we can obtain local observers and two-time correlators, and even real-time local spectral functions. So before we talk about CMPO, let's talk about the MPO representation for the Hamiltonian. So the MPO representation for the Hamiltonian is basically consists of a four-leg tensor. So if we put all the local terms in the Hamiltonian in this four-leg tensor, and we contract all the virtual legs, we can recover the matrix representation for the original Hamiltonian. So this is the basic spirit of this MPO representation. And you can see that to construct, there is a very standard way to construct these MPO representations for the Hamiltonians. And basically, we only need to take the local terms from the Hamiltonian and put that into our local tensors. And then we can obtain the MPO representation. After that, we can make use of the onsides of the matrix product state for our ground state. And the ground state search method is basically to optimize the energy of this matrix product state and minimize this cost function. So this is the basic spirit behind a very rough spirit behind the Yamaji method. And so let's move on to consider the imaginary time evolution operator as an MPO. So interestingly, if we only keep the first order terms in this time evolution operator, we can see that there is also a very compact form for this MPO representation for the evolution operator. And here we take the long-range interacting DC model as an example, and you can see that all these terms can be correspondingly put into this local tensor of this MPO representation. And you can also discover that actually there is a one-to-one correspondence between the MPO representation for the Hamiltonian and the MPO representation for this imaginary time evolution operator. So after we obtain this evolution operator, we can stack them in the imaginary time direction, and then we can obtain the partition tensor network representation for this partition function. And as we mentioned before, we are going to make use the idea of the transfer matrix, so that we can take this red column here from our partition function tensor network, and we will going to try to find this the dominant eigenvector and the dominant eigenvalue for this transfer matrix. After that, we can obtain the partition function at the thermodynamic limit. So as we can see, actually this transfer matrix is also an MPO, and if we take the continuous time limit in the imaginary time direction, this MPO will become a continuous one. So we call that CMPO, and the boundary MPS that we used as the ansatz for the dominant eigenvector naturally becomes the CMPS, which is originally proposed to describe the ground state of continuous systems. And the thermodynamic problem basically is reduced to the rational problem in our CMPO method. We only need to optimize the parameters in this CMPS and then maximize this overlap maximize this cost function. And after that, we can obtain a very good approximation for the dominant eigenvector for this transfer matrix, and we can obtain all the thermodynamic properties of the system. So this is the basic setting of our CMPO method. And to do the so in our simulation, we can calculate very many kinds of different quantities, like the thermodynamic quantities. So here we present a few numerical benchmark results. So this is the CMPO simulation result for the specific heat in the XYZ model. This model contains two XY the XY interactions and also a ZZ coupling between the nearest neighboring spins. And for the different choices of this anisotropy, we can perform our numerical simulation. And so here at this delta zero limit, this model is reduced to the XY model, and it can be exactly solved by transforming this model to the free fermions by Jordan-Wigner transformation. And by comparing the exact solution of this XY model and our numerical simulation, we can see that there is a very good consistency between our numerical result and the exact solution. And so other than thermodynamic limit, thermodynamic quantities, we can also calculate like the two-time correlators using our CMPO method. To calculate this quantity, basically we only need to insert two different local operators into our CMPO representation. And then we can make use the boundary MPS that we have optimized to calculate these correlation functions. So this is again the simulation result in the XYZ model. And you can see that there is a very good consistency between the numerical result and the exact solution. And also, if you look at this expression more in more detail, you can find that there is something here, this K matrix that plays a very similar role of the original Hamiltonian. So this K matrix is some intermediate result obtained from the local tensors in the boundary CMPS and the CMPO local tensors. And from this K matrix, we can actually obtain an approximation for the original Hamiltonian, and use this effective Hamiltonian. We can also calculate some local dynamical quantities with our CMPO method. Basically, we only need to use the K matrix, which is obtained from our local tensors, as an effective Hamiltonian. And this K matrix only has a very small bound dimension, relatively small bound dimension. So we can actually exactly diagonalize this effective Hamiltonian and obtain the local dynamical quantities, obtain the dynamical properties of this effective Hamiltonian. And unlike the thermodynamic calculation, actually the real-time dynamics result is not so satisfactory, at least for these large omegas, the large frequencies. And here, this is again the simulation result in the XAZ model, and you can see there is the inconsistency between the exact solution and the numerical simulation results. But if you look at the low frequency limit, actually we can see the result is still satisfactory. So we think this calculation for the local dynamical quantities should be effective, at least qualitatively, at the low frequency limit for these local dynamical quantity calculations. And so we also perform the calculation for the transfer field Ising model on a quasi one-dimensional lattice. So here we directly work in the low frequency limit and calculate this spectral function. And we can see that this model has the critical field if it's put on the two-dimensional lattice. And on the two sides of this critical field, we can indeed see very qualitatively different behavior of our numerical simulation results. So basically, we say this calculation of the local dynamical quantity is at least a very good qualitatively can give you very good can give you qualitatively good results for these calculations. And so let's move on to the second part of our talk. So we will apply our CMPO method to the 1+1 dimensional nonlinear signal model, which has the topological theta pi term. And the nonlinear signal model, the Euclidean action of the nonlinear signal model looks like this, and it consists of a field operator, which is actually a unit vector that lives on the unit sphere in the three-dimensional space. And the first term here, the blue term, is basically represents the coupling between these vectors in the two directions, the x direction and the tau direction. And there is also a theta term. This theta term is basically a surface term. You can interpret that as the surface contribution to the action. The surface contribution comes from the trajectory of this unit vector when you move around the two-dimensional space by tuning your x and tau, and the surface term obtained from this covered by this trajectory basically gives the contribution in the theta term. And this model becomes interested in the high energy community because it shares a lot of common features with the 3+1 dimensional gauge theories, and it is also very relevant to the strong CP problem in the high energy physics. From the condensed matter side, people have become interested in this people have become interested in this nonlinear signal model, probably starting from the Haldane conjecture. So in the early 1980s, Haldane proposed a conjecture based on his work on the mapping between the 1+1 dimensional nonlinear signal model and the anti-ferromagnetic Heisenberg spin chain. So for the anti-ferromagnetic Heisenberg chain with integer spins, Haldane conjectured that found that this model can be mapped to a nonlinear sigma model with no theta term. And at that time, people know that this nonlinear sigma model with no theta term actually has a very finite correlation length. So Haldane conjectured that the integer spin Heisenberg model should be gapped. And on the other hand, for the half integer spin anti-ferromagnetic Heisenberg model, Haldane mapped that to a nonlinear sigma model with the topological term theta equals to pi. And since at that time, people also know that this anti-ferromagnetic Heisenberg model is gapless. So Haldane then conjectured that the nonlinear sigma model with the theta equaling to pi is also massless. And it is later proposed by Shankar and Reed in the early 1990s that this model actually is gapless for all the coupling constant from the weak coupling limit to the strong coupling limit. So actually there is the RG flow from the weak coupling limit at G equals to 0 to the RG flow to the fixed point at G equals infinity. At the G equals infinity limit, this model is well described by the West-Domino-Witten CFT with the central charge 1. And to verify these conjectures for this nonlinear sigma model with theta equaling to pi, people have been considered about numerical simulations for this field theory model. And the most straightforward way is to discretize the two-dimensional space of X and tau, and then simulate a classical system. However, actually, if you work that into the most straightforward way, then you will find that there will be a sign problem for this if the topological term is non-zero. So although there is various methods that proposed by the Monte Carlo people that you can actually work around this sign problem in this problem, but we should say that these workaround algorithms are all very complicated, and it cannot be very simply extended to other models and in other simulations. On the other hand, the tensor network, as we mentioned before, it has no sign problem and should be very appropriate for these kind of simulations, even for non-zero topological term. And also, in the tensor network simulations, we can also explore the regimes like the non-zero chemical potential and the real-time dynamics regime, which is not accessible by the Monte Carlo simulations. So in our calculation, we will work in the Hamiltonian formalism. Basically, we will interpret the x dimension as the spatial direction of a quantum system, and the tau direction as the imaginary time direction. And it is well known that for the nonlinear sigma model with no theta term, this model is corresponded to the quantum rotor model. The quantum rotor model basically describes a system consists of different quantum rotors, and the first term in this quantum rotor, it describes the rotation of these rotor terms. And the second term basically represents the coupling between the nearest neighboring rotors. And there is a standard commutation relation between the angular momentum operator and the rotor operators. And it has been well known that this model is actually the Hamiltonian formulation for the nonlinear sigma model with no theta term. So although this is a well-defined model, but you cannot use that directly in the tensor network simulations because this model consists of continuous degrees of freedom. So to enable tensor network simulations, we have to find a discretized basis for this quantum rotor model and then find its matrix representation. To do that, the most natural choice is to use the angular momentum basis. Basically, we only need to choose the eigenbasis of this angular momentum operator and then represent all the terms under this basis. And very obviously, the kinetic term will become diagonal under this basis. And to represent the interaction term under this basis, we only need to decompose this coupling term into different spherical tensor operators. And then we can make use the well-known formulas in the spherical harmonics to represent the interaction term under this angular momentum basis. So basically, after you go through all the calculations, you only need to calculate the coupling. Calculate the nearest coupling term, you only need to calculate a few weakness region symbols and then put that into a program, and then you will obtain your coupling term in this angular momentum basis. So this is for the nonlinear sigma model with no theta term. Now let's move on to the nonlinear sigma model with the theta term, with the theta pi term. So interestingly, it is found by Shankar Reed at the 1990s that actually you only need a very small modification for the quantum rotor model to represent the nonlinear sigma model with the topological theta pi term. Basically, you only need to modify the original angular momentum to a modified angular momentum operator by attaching a magnetic monopole to this angular momentum operator. And after this modification, the commutation relations will still hold. This basically means this is still a well-defined angular momentum operator. And after that, you also have to modify. You also have to specify the coupling between the rotors to be an anti-ferromagnetic one. After that, you will see that actually this model is corresponding to the nonlinear sigma model with the topological pi term. So to understand this, we can look at this very rough explanation for this correspondence. So putting a magnetic monopole at the center of the quantum rotor basically means you will generate a uniform magnetic field at the sphere of this unit vector for the quantum rotor. And since we have employed the anti-ferromagnetic coupling between the rotors, the nearest neighboring rotors will become almost anti-collinear between each other. So the surface term comes from the magnetic field at the unit sphere will almost cancel with each other between the nearest neighbors. So there will only be a ribbon contribution covered by the trajectories of different rotor points at the unit sphere. And if we decompose the quantum rotor into the fast moving and the slowly moving term, and then integrate out this fast moving field, we can see that actually the surface term from the slowly moving term by this magnetic field will contribute to the nonlinear sigma model theta term, which is, as we mentioned before, also a surface term. So this basically gives the very rough explanation to why this model can be corresponded to the nonlinear sigma model with the topological theta pi term. And then we can follow the original way to construct the matrix representation. Basically, we need to find the eigenbasis or a different modified angular momentum basis for this modified angular momentum operator, and then represent the coupling term into this under this modified angular momentum basis. Unfortunately, we found that this is already known in the literature. So basically, for the angular momentum attached with the magnetic monopole, there is the existing solution for that. This is known as the monopole harmonics. So basically, the kinetic term will so we will follow the similar way as we treat the nonlinear sigma model with no theta term. So the kinetic term will become diagonal in the under this basis, and the interaction term can be decomposed as different as the sum of different spherical tensor operators, and then we can obtain the matrix elements of these spherical tensor elements, spherical tensor operators by calculating by calculating its expectation value under the monopole harmonic basis. So you can see that this calculation process is very similar to the case without theta term. And for our practical simulation, actually this is not still not enough, because you can see that this is actually an infinite basis. So for tensor network simulations, we also need to truncate this monopole harmonic spaces. Basically, you need to put some truncation into this onto this basis. Otherwise, it will become infinite dimensional. The local Hilbert space will become infinite dimensional. And actually, at this point, you can do all the tensor network simulations that you know for this model. You can calculate the ground state properties, finite temperature properties, and even the real-time dynamics using the real-time evolution. Here, we only make use our CMPO method to study the finite temperature properties of this model. And basically follow the routine that we described before. We only need to decompose this Hamiltonian and put the local terms in this Hamiltonian into the different blocks of these Fourier tensors. And then we can obtain the CMPO representation for this for the partition function of this for this nonlinear sigma model with the theta pi term. And then we optimize the boundary CMPS to obtain the thermodynamic properties of this system. And as we mentioned, we want to verify that this model is critical for all the parameters, for all the coupling constants that we use. So here we calculate the free energy for different choices of this coupling constant, and we also compare the different results from by truncating by using different truncating schemes for the local Hilbert space, as we mentioned. And it is well known by the CFT people that if the system is described by a CFT, then the free energy density will have a universal scaling with respect to the linear scaling with respect to the temperature square. And you can see from our numerical result, this is indeed the case for our calculation results. For all the coupling constant that we use, and for all the truncation of the largest angular momentum that we use, we all obtain the linear dependence between the free energy and the temperature square, which verifies the critical behavior of this model for all these coupling constants. And we can also see that by increasing the truncation by increasing the largest angular momentum that we use to truncate the local Hilbert space, we can see a convergence between these numerical results by increasing this L max. And we also calculate the temporal entanglement entropy of this model. So since this model, if this model can be described by a CFT, then we can think the boundary MPS as the ground state of this of the SAM CFT, and then we can partition this boundary MPS into two parts, and then calculate the entanglement entropy. This will follow the scaling of the entanglement entropy for the ground states in CFT, and in our calculation we only need to check the scaling of the entanglement entropy with respect to the log of this temperature of this inverse temperature. And here we perform our calculation for all the for different coupling constants, and also for the different largest angular momentum in our simulation. Now we can see that there is also very good linear dependence between the entanglement entropy and this log beta. And from this calculation, actually we can also obtain this central charge from our by linear fitting our numerical data, and then we can see that there is we can obtain the central charge for the different values of this coupling constant, and this horizontal line here because is attributed to that this L max equaling to 1/2 is actually not very effective because it directly reduces this model to a spin 1/2 Heisenberg model. But for the more effective truncations, we can see that there is a monotonically change of this central charge with respect to the coupling constant, which is actually consistent with the C theorem, because the C theorem states that your central charge should decrease monotonically with respect to the renormalization group flow, and this is our result is consistent with the C theorem. So let me give a summary. So in our work, we proposed a CMPO method for studying quantum states at finite temperature. Our method is can work directly in the thermodynamic limit and the continuous time limit, and also can treat the short range and long range interaction systems on the equal footing. And we can obtain observables and the true time correlation functions and even local spectral functions for the real-time dynamics. And we also we also perform the CMPO calculation for the 1+1 dimensional O3 nonlinear sigma model with the topological theta pi term. So to do that, we obtained a Hamiltonian formulation for this nonlinear sigma model with theta pi term, which is basically a quantum rotor attached with magnetic monopoles. And we obtained the matrix representation for this quantum rotor model, which enables all kinds of tensor network simulations. And in our finite temperature calculation, we calculated the free energy and the temporal entanglement entropy, which verifies the massless nature of this model for all the coupling constants. And we also are able to directly extract the central charge from our calculation. So as an outlook for the CMPO methods, we plan to extend that to the 2+1 dimensional quantum models. So basically, we can use this method for the true two-dimensional system, which is infinite in both two directions. And we can also think of its extension to the real-time dynamics. And also for the nonlinear sigma model simulation, we can think about more effective simulation near the weak coupling limit, because you can see that actually the convergence with respect to the truncation is not very good. And so there are different ways to do that. Either we can perform some scaling analysis with respect to the Lmax, and or we can come up with better choices of this basis at this weak coupling limit. Thank you very much.
Okay, thank you very much for interesting talks. So now this talk is open. Is there any question or comments? Okay, Okubo-san, please.
Thank you very much for your interesting talk. Can I ask the technical details of your continuous MPS?
Yes.
So I wonder how to take a continuous imaginary time limit in your simulation. So is it possible to take that limit
You mean
exactly?
how to take the
Yeah.
So you mean how to take the continuous time limit?
Yes. Yes.
Technically.
Yes.
So so let me see. So actually you can see there is the epsilon dependence in our CMPO. This epsilon is the time discretization.
Yes.
And in traditional ways to do the simulation, you will choose the finite value for this epsilon, and at the end of the calculation, you will end up with some finite error in your simulation.
Yeah. Yes.
But if we keep this epsilon in our calculation and don't take a finite value for that, but at the end of the calculation, if you take epsilon to zero limit, and then you can actually find that this limit can be analytically taken. And after that, if you look at this calculation, this basically means you have to contract this tensor network, and this expression becomes some form like this. This is the identity matrix, and plus some linear term with respect to the epsilon, and this is the power to the beta over epsilon terms. So you can actually analytically take this epsilon to zero limit at this calculation in the calculation process, and after taking the continuous limit, this will becomes a trace of exponential. Then the epsilon will disappear basically after this continuous limit, and you can just evaluate these expressions. So without looking at the finite values of this epsilon.
Oh, okay, I was a little bit confused. So to calculate the dominant eigenvector by MPS, so I guess that you need to assume the finite epsilon. Is that correct?
No, actually, there is we make use of this CMPS ansatz, which is quite different from the ordinary MPS. Basically, in the CMPS local tensor is just although we didn't have a formula for that, unfortunately, but I mean, actually, this CMPS is also composed of this epsilon in its parameterization, just like this CMPO parameterization. So, if you, so actually, you can take the epsilon into your calculation, and then you can safely take the limit of this epsilon to zero limit.
Okay. It's very interesting. Thank you very much.
Thank you.
So I have a similar question to the Okubo-san. So for the case of the total decomposed two-dimensional system, the transfer matrix has a discretized in the imaginary direction. And if you take a low temperature limit, the number of lattice point around the imaginary time direction increases, which makes numerical computation difficult. So in your CMPO approach, what happens if you take a low temperature limit? What is the source of difficulty in numerical computation?
Yeah, the numerical difficulty of this low temperature calculation actually is governed by the entanglement in the time direction. So, for example, if we can take the critical system into our into our consideration, then this entanglement in this time direction is actually proportional to the log of this of beta, which is the length in the imaginary time direction. So basically, in principle, in the low temperature limit, we can increase our bond dimension correspondingly with respect to the log beta.
So you need a much more bond dimension in low temperature.
Yeah, larger bond dimension. Yes.
I see. Thank you. So is there any question or comment? Okay, Lin-san, please.
Hi, thanks for the nice talk. Just one follow-up question on this slide. So the way you find the dominant eigenvector is by kind of DMRG way of minimizing this stuff. Is it like that? Does it also work for CMPS in that way?
Actually, we not exactly. Actually, we make use of the because we for the CMPS we cannot directly employ the original DMRG procedure for the CMPS optimization. And in our calculation, roughly speaking, for example, for the simplest case, if the transform matrix is Hermitian, then the left dominant eigenvector and the right dominant eigenvector will be the same. And then we can calculate the gradient for this cost function and use the gradient-based optimization methods. We can optimize the parameters in the CMPS, which is used to parameterize the CMPS. And then based on the gradient-based optimization, we can optimize the parameters in the CMPS to minimize this to maximize this cost function. This is how we optimize the CMPS. This is different from the DMRG method.
Okay, and I've heard people used to say that CMPS are a little bit hard to handle, like maybe also in terms of like you have to do this gradient descent methods to tune it. Is it always the case that throughout the whole parameter range and different models that you tested, is it always easy to get to the correct like ground state of this problem, or like finding the correct CMPS of the fixed point?
I should say technically there is difficulty in that because this optimization process is highly nonlinear, and you will be easily trapped into local minima before you get to the ground state, true ground state of this optimization. And we have come up with a few procedures to make the process easier, but in general, we cannot ensure that. I should say, for most cases, we can still obtain very satisfactory results, but in principle, you cannot ensure this is the true ground state. You will always have the problem of being trapping in the local minima. In our simulation, actually, we make use of the power method before we start our gradient-based optimization. From the power method results, we can get much closer to the true ground state. And then, if our initial state actually resides in the regime that is governed by the global minima, then we can our numerical results from the gradient optimization will be much improved after that. But
I see.
but that is still no guarantee for the global for the global minimum. Yes.
Okay, I see. Thank you.
Yeah. Thank you.